Welcome everybody to chapter 12, vector valued function. In the previous chapters, we learned that a space curve was defined as the set of ordered points f of t, g of t, z of t, together with their defining parametric equations x equals to f of t, y equals to g of t, and z equals to h of t. Before looking at examples of space curves, a new type of function called a vector value function is introduced. This type of function maps real number to vectors. It is written as r of t equals to f of ti plus g of tj plus h of tk. Let's look at an example of sketching a space curve. According to the question, we know that the parametric equations are x equals to 4 cosine t and y equals to 4 sine t. Based on the trigonometry identity as cosine squared t plus sine squared t equals to 1, we can obtain x squared plus y squared is equal to 16. This means that the curve lies on the right circular cylinder of radius 4, centered about the z-axis. To locate the curve on the cylinder, you can use the third parametric equation z equals t. According to the figure, note that as t increases from 0 to 4 pi, the point xyz spirals up the cylinder to produce a helix. We can also represent a graph by a vector value function. Let's do example 4. Like many other questions, we need to choose our own parameter, and the natural choice of parameter is usually x equals to t. Since y equals to x squared and x equals to t, we get y equals to t squared. And then we move x squared over 12 plus y squared over 24 to the right side of the equation, and we obtain z squared over 4 equals to 24 minus 2 times t squared minus t to the fourth power over 24. And eventually we get the value of z, and at this moment, x, y, z can be represented by t. Then we can write out the vector value function r of t equals to ti plus t squared j plus the square root of 24 minus 2t squared minus 2 to the fourth over 6k. The second part of section 12.1 is about the limits and continuity of vector value function. When you take a limit of a vector value function, you just need to find the limit of every single component in the vector value function. What it means is that when you take a limit of r of t as t approaches to a, you need to find the limit of f of t as t equals to a, and limit of g of t as t approaches to a, and limit of h of t as t approaches to a. To test the continuity of a vector value function, you just need to find out if limit of r of t as t approaches to a, if that limit is equal to r of a. If it equals to r of a, then the vector value function is continuous. Let's take a look at example 5, continuity of vector value functions. The first thing we can do is to plug 0 equals to t into the function, and we get r of t equals to aj plus a squared k when t equals to 0. The second step is to find the limit of this vector value functions. as t approaches to 0, r of t also equals to aj plus a square k, then we can say the vector value function is continuous at the point t equals to 0.